Okay, welcome to Unit 19 and 20. We introduce a new object. The object is called a vector field. And it's very exciting, new thing. What we do is we attach at every point in the plane or every point in space, we attach a vector. So I wrote you down here an example of a vector field, quite a complicated field. Maybe I can project in the actual vector field here, but what we can do is at every point, for example, at the point 0, -1, what we have is here -1 and then 1. So it's -1, 1. So in this case, the vector is here. So that's quite a tedious task to do in general, to draw all these vectors and to have a picture of the vector field. A computer can do that very well. For simple vector fields, we can do that. We will just look at examples. One of the visualization tools to see a vector field better is to draw a flow line. So what we have is at every point, we just look at the vector, and that's our velocity vector for a curve. So what would happen is this curve would then go something like this. This is a flow line. Actually here, this is a very important example here of a vector field which we can completely understand. At every point xy, we just attach the vector xy. So this is like that. And then further away it's getting bigger, and closer it is getting smaller. And the flow lines which we have are just these lines here. So these vector fields appear in many places, like there are velocity fields, like in fluid dynamics. There is force fields, like in mechanics. Gravitational force field, for example, is a vector, it points down. There are magnetic fields. You can look at this vector field. This is something in space. So we have these flow lines which allow us to visualize the vector field. Here's another important example of a vector field. -yx. If you have taken some single variable calculus with differential equations, you might have seen slope fields. And a very important class of vector fields are gradient fields here, fx, fy, if you have a function fxy. And these gradient fields will play an important role here. If you have a gradient field, you have a very nice way to compute with that vector field. So if you have this vector field here, and we want to write it as a gradient field, I just write this. This is fx and fy. So one of the things you can do is you differentiate the first one with respect to y and the second one with respect to x. And by Clairaut, you get the same thing. So qx minus py is equal to 0 is necessary for a gradient field. And actually, we'll see next week, it's actually also sufficient if the vector field is nice. So in this case, if you take qx minus py, not 0. However, in that case here, we can find a function. And we will do that in class. How do we find a function here? Essentially, what you do is you take this equation and you integrate. Then you get xy plus x cubed third plus a constant which can depend on y. And then when you check with the second equation, you see that you have also to add y to the 4/4. So that's fxy. So the left vector field here was a gradient field. It passed the Clairaut test, and we could find a function f. This case here, this did pass the Clairaut test, and we have no chance to find a f such that this is fx, fy. Welcome to this unit 20. We look at line integrals, and it's something related with work. If we have a force and multiply it with velocity, then what we get is power. And if you look at this, integrate this over time, what we get is energy, a heat engine. It makes use of this mathematics of line integrals. But here's the definition. What we have is we have a vector field and we have a curve, and what we do is at every point we compute the force field. In this case the force field is like that, and then we compute also the velocity vector, which is here, and we take the dot product between them. So if you are going with the field, then you gain energy. If you go against the field, you are losing energy. And one of the most important theorems is the fundamental theorem of line integrals, which generalizes the fundamental theorem of calculus. That's the first really generalization of the fundamental theorem of calculus. So it tells you that if you have a gradient field, it only works for gradient fields. So if F is a gradient field, then when we compute the work along the curve, what we have is just the end energy, potential energy value minus the initial potential energy value. And it's something very nice to prove. I invite you to look at this. I'm just with a chain rule. This is just the d over dt of f of r of t. By the fundamental theorem of calculus, this directly follows. So in this case, we have a line integral of a vector field which is not the gradient field, so we cannot use the fundamental theorem. So let's just maybe do that quickly, and you can see a little bit of intuition what happens. If you go along the circle here, you are losing some energy here, but not so much than what you gain here, because here the vector field is much bigger. We take the same curve, but we take this vector field here. Now what happens with this vector field is this is a gradient field. We have learned how to compute the potential. So this is equal to fx, fy, and so when we integrate, we get f is equal to minus xy, and actually that just works. So by the fundamental theorem, the integral here along this curve, c, f dr, is just f of 0, 0. It's actually f of, let's just call this point A, minus f of point A, because this is the same point. If you have a vector field which is conservative and you go along a closed loop, you cannot gain energy from it. You cannot gain energy from nothing. So this is not a perpetual motion machine, because we have put some energy in here. We have put hot water here. So this energy has been used to generate work. But people have tried, of course, since antiquity, to find perpetual motion machines which give you energy out of nothing. So it's a matter of fact that all fundamental forces which we know are conservative. There are gradient fields. And but this is kind of an attempt using magnets. Let me just show you how that works. So you get attracted here because minus and plus gets attracted. But once you are here, the plus is here, the minus here, you get pushed along. So what it is kind of pill or ship is going along here all the time. So it's I myself came up once as a kid with this tube. There are many variants of that. It's not actually original. One has since the antiquity one has such examples. But what it is, so there is a valve here, a valve here. This is water. You have some pebble which is inside the water here. That pebble goes up inside the water because of buoyancy, and when it is here, it goes down. It is by gravity. You have also these visual riddles put forward by Escher, where you have things which are always going down, like a waterfall where the water is always going down and falls down. So, but that's it. That's Unit 20 about line integrals.